Or the idea is, what do you do when infinity appears somewhere in the integral? So one of the first big ideas that you encounter when you first start taking calculus is this notion of infinity. What do you do when there's an infinity in the calculation? And we're going to come back to that idea in this topic. Okay. So first, there are two ways that you can have infinity. So the first thing we're going to look at is what happens if there's infinity as an x value. So in this case, what that means is your boundaries of integration, one of your boundaries is infinity. So what does that mean? So in this integral, so let's say we just treated this integral like a regular integral. You take the antiderivative, you get negative x to the negative 1. Okay, what does it mean to plug in infinity?
Are you taking the limit?
What do you mean? If you plug in infinity, if you plug in infinity here, it's going to be a 0. Because it's constant over.
Right. So that already starts to give you an idea of what does it mean to plug in infinity to an expression. This is something that we've actually seen a little bit before. But I want to expand this idea. We could also interpret what that means graphically because we know what an integral is. We know what an integral means graphically. So another way to think of this is if f prime equals x squared, what is the value of f of x at infinity? Right. So so graphically, what does this mean that we're doing? It means we're looking at a slope field. We know what f prime is. We want to say something about f. Well, this is what it looks like. So do you think that we'll be able to say something about the value of the function at infinity?
Yeah.
And how do we do that?
It looks like it's approaching the line.
So the other way to interpret integrals is to say you have a function and the integral is finding the area. Okay, well what does it mean to take the area under an infinitely long curve? So here's that picture. And of course, the other graph is the graph of the area function itself. Okay. So we want to know what happens eventually, the target value as that endpoint approaches infinity. So how do we say that mathematically?
Limits.
It's a limit, exactly. Okay.
Said that other.
So let's take a look at how we set that up. So you start with your original integral, and we say that since infinity is really there, we know what this means is this means to take a limit. So we set that up. Ooh. Sorry, a bit of a typo there. Let's fix that. Okay. Okay. So first of all, we know that it's better to write things with negative exponents, so I did that. And instead of saying we're integrating from 1 to infinity, what we say is we know that what this really means is a limit. So it's the limit as b goes to infinity of the integral from 1 to b. So formally, this is what we have to say. So now we can just go ahead and do the integral. So the integral of that is negative x to the negative 1. We evaluate it from 1 to b, which just means negative b to the negative 1 minus negative 1 to the negative 1. So now we have to evaluate that. So straightening out some of the things, straightening out that algebraically, it's 1 minus 1 over b. Now what is the limit of that as b goes to infinity? Well, 1 over b just goes away, it goes to 0. So the entire expression equals 1. So formally, that's the idea. And as we saw, if you think of the graphical interpretation of the integral, this makes sense. Both in the slope value picture, you can see that the value this function wants to approach is 1. In other words, as a limit. And second of all, the area is accumulating, and if you kind of eyeball it, you can see that it's going to a value of 1. Okay. So, anytime an integral has either positive or negative infinity as a boundary, first step is set it up as a limit. Then go back to just doing the integral like you normally would. And then the last step is evaluate the limit. So there's just an extra first step and extra last step involving limits. So if the limit exists, like in this case, the integral is defined, or we say it converges. If the limit does not exist, the integral is undefined, or we say it diverges. Of course, some of this you've seen before just from studying limits themselves. So here's another one. So the integral from negative infinity to 0 of e to the x dx. So what do we do?
Limit a to 0 of e to the x as limit goes to infinity.
Okay. So basically, so I wrote it as the limit as a goes to negative infinity of the integral from a to 0 of e to the x dx. So you'll notice one little thing that I did is we've always used the notation where we say that the lower limit is a and the upper limit is b. And I'm just going to stick with that because that just makes sense for us, and we're used to that. Okay. So now we have it set up as a limit. Now we can just do the integral like we normally would. Integral of e to the x is e to the x. So you plug this in, you get e to the 0 minus e to the a. Okay. So first of all, what is e to the 0?
1.
E to the 0 is 1. What about e to the a as a goes to negative infinity? What is that?
So that would be reciprocal. That would be 0.
Right. So this is, if again you could think of this as e to the negative infinity. Well, what does that mean? That just means 1 over e to the infinity. So that's going to 0. So the answer is 0.
And if it wasn't negative infinity,
Should be
it would
1.
just be.
No, it should be 1.
Ha ha. Indeed. Okay. 1.
If it wasn't negative infinity, then the solution would be just infinity, or negative infinity.
So what the answer that you get simply depends on the limit that you're evaluating in the problem. Right. So let's take a look at this next one, for example. The integral from 0 to infinity of Cossacks Dx. So what's the first thing you have to do? Right. You have to set this up as a limit. As b goes to infinity, integral from 0 to b, Cossacks Dx. So integral of cosine x is sine x. It's got sine x going from 0 to b. So we've got the limit as b goes to infinity of sine b minus sine 0. Now what do we do with this limit? What is the limit? What do we know about the sine function? What do you? So sine of 0 is 0. That's right. But what about sine of b with b getting bigger and bigger going off to infinity? What is the behavior of the sine function? It keeps going. It keeps repeating and cycling back and forth, up and down. So does it have a limit value?
Undefined.
Yeah. There's no limit value or target value.
So
It's undefined. So this is just a matter of remembering how to do limits. Okay. So one slightly fun case is if both boundaries are infinite. If both boundaries are infinite, you have to make a limit for each one. So in the following way. The limit from negative infinity to infinity of 1 over 1 plus x squared dx. So you have to take the limit for the lower boundary, and you have to take the limit for the upper boundary as well. So limit is a goes to negative infinity, limit is b goes to infinity, the integral from a to b of 1 over 1 plus x squared dx. So now that we've put the limits in, now we can just take the integral. The integral of that naturally is arctan. And so now we have to evaluate it. So what you wind up with is arctan of b minus arctan of a. And each one is its own limit. So in the first case, you have the limit as b goes to infinity of arctan of b. And in the second case, you have the limit as a goes to negative infinity of arctan of a. Now, I skipped over some technical details about things that you're allowed to do with limits, but suffice to say that everything is correct. And the most important thing is just to understand that you need to take the limit on each one separately. And that's the important idea, which I think is a clear idea. Okay. So at this point, you have to know something about the arctan function. So if you don't remember arctan function, think about tan function. What does the tan function look like? There's a bunch of them, and it just goes from negative infinity to infinity, and it repeats itself every time. So arctan takes one of those, and it flips it on its side. So the thing that you have to, or in other words, arctan looks like this. So the only thing you have to remember is, okay, what's this value, and what's this value? And you could figure that out if you think about the tan function. Right. So tan is, so the asymptotes for tan are when x equals negative pi over 2 and pi over 2. So similarly, if you flip it around, think of the inverse, these asymptotes will be at y equals negative pi over 2 and y equals pi over 2 for arctan. So you get pi over 2 minus negative pi over 2, and that gives you pi. So if both boundaries are infinite, you have to take a limit for each one. And I just want to make this comment that the notation that I use to write this down is different from the standard textbook notation, but it's equivalent. And the truth is that mine is quicker and more efficient. And it also highlights the point that the important thing is to take a limit at each boundary, which is all you have to do. So that covers what do you do with an integral that has infinity for an x value. Next. What do you do when what you're integrating has an infinite y value? Or in other words, the function goes to infinity. So the basic case is at one boundary the function is infinite. So once again, we're going to take a limit. So for example, what if we're doing the integral from 0 to 1 of 1 over the square root of x? So where is there a problem? There's a problem when x equals 0. So at that value, the function is infinite. So you might think, oh, the function goes to infinity, therefore you can't do the integral. And in fact, that's not the case. And that's what we're going to see using limits.
Is this like the case where...
Okay. So we have to set this up as a limit because the function is undefined at x equals 0. So that's where we take the limit. So you take the limit as a goes to 0, the integral from a to 1 of 1 over the square root of x dx. Anytime you have to deal with infinity, you set it up as a limit at that spot. In this case, the spot is where x equals 0, so that's your limit. So in order to do this integral, we know we want to rewrite this as a rational exponent. So it's just the integral of x to the negative half. Integrate that, you get 2x to the half. So if the limit as a goes to 0 of 2x to the half from a to 1. So you plug it in, you just get 2 times 1 to the half minus 2 times a to the half. Now, can we evaluate that limit? When you take the limit, what do you get? Yes, because the part with the a in it, you've basically got the square root. You've got square root of 0, which is just 0. So then all you need is 2 times 1 to the half, which is just 2.
I see how we can do it.
Okay. So one little comment. To be precise, since the undefined x value is a boundary, this is really a one-sided limit. So that's what that little plus, if you're wondering what that little plus was, it means we're really taking the limit as a goes to 0 from the positive side. And if you think about which x values we're concerned with, this makes sense. We're only concerned with x values from 0 to 1. So we really only care about what are the x values on the positive side going to 0. So this is a technical detail, and for the purposes of this course, Calculus 2, that detail will not affect the outcomes of our problems. So you don't need to worry too hard about it. Okay. So next, might be wondering, what happens if the undefined x value is in the middle of your interval? Split your integral into 2 separate integrals. So for example, the integral from -1 to 8 of x to the -1/3. Where's the problem value?
That's between the -1 to 8.
Right. Which number?
0.
The problem value is at 0. You have to split it up at 0. So the integral from -1 to 0 of x to the -3 dx plus the integral from 0 to 8 x to the -3 dx. Now why do we split it up there? So now on each one there's a problem, there's an undefined value at the boundary, so each integral needs to be rewritten in terms of a limit. And now this is just the previous problem.
You're not. Will you ask us like more complex cases when we do a?
So each integral needs to be converted to a limit. So the first one, the improper boundary is on top. So I said limit as b goes to 0, integral from -1 to b. And the second one, the improper value is the bottom boundary. So the limit as a goes to 0, integral from a to 8 of x to the -3 dx. Okay. So now we can evaluate these integrals. And it's 3/2 x to the 2/3. And then on each one, you plug in on the boundaries. And notice that in each case, we still need to evaluate the limit. So what is the limit of 3/2 b to the 2/3 as b goes to 0? It's 0. It's 0 to some power. It's 0 to some positive power. Excuse me. 0 to some positive power, so it's 0. And then what about on the other side? Limit as a goes to 0. again, 0 to some positive power, 0 to the 2/3 is just 0. So you get 0 minus 3/2 plus 6 minus 0. Work it all out. You get 4.5. So this is kind of crazy. You've got this point where the function is infinite in the middle, but yet somehow you can do this calculation. So it's a really crazy idea we'd actually spend a lot of time on, but we're only going to cover this basic idea. The fact that we can use limits to actually uncover this actual value. So I want to close this by revisiting an integral that we've seen before. In one of the earlier lectures, I gave you this integral and I said, hey, let's do this. And at that time, we didn't know about improper integrals. We didn't think about improper integrals. We just went ahead and did the integral and plugged in numbers. And I think you get something like -1/12 or something like that. I don't know.
I think you give it on the exam.
Something like that.
No.
I'm pretty sure.
Talked about this in class.
No,
So now we're going to see that we now have the actual mathematical machinery to deal with this problem. So how do we do this?
0, 3 to -3 to 0 and 0 to 2.
Right. We've got to split it up. So the integral, because the problem value, the value where it's undefined is at x equals 0, so you split it up there. Integral from -3 to 0, x to the -2, and then plus the integral from 0 to 2, x to the -2. And then you convert it to limits at the undefined value. And then when you do that, you wind up with the limit as b goes to 0 of -b to the -1. So what can you say about that limit? What is 0 to the -1 power? If you like to think of it that way. It's 1 over 0, it's undefined. Exactly. And then the same thing on the other side as well. You wind up with a, the limit of a, limit as a goes to 0, a to the -1, also undefined. So we've got an undefined limit, so the integral is undefined, the integral diverges.
Is there a graphical representation of